Today we're going to be looking at transformed power functions. So we've already looked at transformations, we've already looked at power functions, and we're basically going to put those concepts together. So we're going to start with a review of basic power functions. This is going to be stuff that we've covered in other videos and other sections, and we're just going to review the basic characteristics of the graph shapes of all the basic power functions. And then we've looked at several different transformations. We're going to see how that applies to power functions to obtain a general form for a transformed power function. We're going to look at a couple of different types of exercises we could do with this. Then we're going to talk about direct and indirect variation. We've talked about direct variation before a little bit to give us linear functions through the origin. We're going to now apply that to power functions and see how we can get some specific transformed power functions, ones that just have a vertical stretch or compression. And then we're going to finally talk about power function regression, the same kind that we got from the direct and indirect variation. We're going to see how we can use the calculator to help perform some regression there. So basically we're going to be taking earlier ideas like linear regression, direct variation from linear functions, transformations, power functions, just kind of put all these pieces together. So we're going to start with a review here. Basic power function is f of x equals x to the n, or y equals x to the n. So notice that you just take your input, raise it to a constant power, very simple kind of function, one step. So notice that a positive to any power is positive, so all the graphs have quadrant 1 and none of them are in quadrant 4. 1 to the n power is 1 for all n, no exceptions, so 1, 1 is on all these graphs. That was the only point that was on all of them. 0 to the n is 0 for any positive n, so if n is positive, then we got 0, 0 on the graph, and in fact the graph turns out to be connected or continuous if that happens for positive n's. But if we have negative n or 0 n, they're undefined for 0, and so that gives us a break in the graph when they actually have more than one quadrant. So they all go through the first quadrant, and you can look at the size of n to tell you what the graph looks like in the first quadrant. We have basically 5 different possibilities here. If n is negative, let's start down at the bottom, then we have a vertical and horizontal asymptote of the y-axis and the x-axis respectively, and so this is decreasing and concave up in the first quadrant. So they all look more or less like this when they have negative powers. They do go through the point 1, 1, and then they look kind of like this graph down here. Now if n equals 0, that's a specific n. This one has a hole in the graph, and it looks like I got my hole a little bit in the wrong place. That should be down here, right on the y-axis, but right here where the graph comes in. And so it's this one, when you graph the whole thing, is actually a horizontal line. 0 to anything to the 0 power is 1, except for 0 to the 0, which is undefined. So this does have a break in it. It's not continuous. It has a break, a hole in the graph at the point 0, 1. It does go through 1, 1 in the first quadrant. They all go through 1, 1 in the first quadrant. So notice if n is negative, the function's decreasing in the first quadrant. If n is 0, the function is constant in the first quadrant. And if n is positive, the function is increasing in the first quadrant. But within the increasing ones, we have 3 cases we want to look at. So if n is between 0 and 1, it goes through 0, 0, and 1, 1, but it does it in an increasing concave down manner, something like the graph that you see here in the middle. Whereas if n equals 1, then it's just y equals x. We know that's a straight line, so it's increasing but linear. And if n is greater than 1, it's increasing in the first quadrant, but concave up, going through 0, 0, 1, 1, but does it in concave up manner. So those are the 5 different basic graph shapes you can see for the first quadrant of the graph. Now what does the rest of the graph look like? Well, it depends on what type of power n is, and that's given by this table. Okay? So if n is irrational, or it's a rational number with an even denominator when it's reduced, an odd over an even, then it's only in quadrant 1. Notice what happens with a negative number. If you raise it to an odd power, you get a negative, and you try to take an even root of a negative, you get a non-real number. And so for our purposes here, that's undefined because we're only graphing things with real first and second coordinates. So it's only in quadrant 1, and it will be continuous, but it will not have any symmetry to it. It'll just be the one piece there. Okay? So for positive n's, that means the domain is from 0 to infinity. It does include 0, 0. So 0 is in both the domain and range. But if n is a negative number, okay, then you're only in, or if it's 0, actually, for that matter, the domain is, well, I'm sorry, 0 is down another case. If it's negative, then it's 0 to infinity, not including 0. So it's still first quadrant, but not including the origin if n is a negative number. If n is a positive number, then it does include the origin. But it's only first quadrant in that case. Now, if we have an even over an odd power, where it's a rational power, but it's even over odd when you reduce it, then that's quadrant 1, of course, but it's also quadrant 2. If you take a negative to an even power, you get a positive, and then you take an odd root of that, it's still positive. So, for example, that includes negative 1, 1, as well as 1, 1. And so that's going to include quadrants 1 and 2, and the part in quadrant 2 is a reflection of the part in quadrant 1 over the y-axis. So the graph will have y-axis symmetry. Okay? And so the domain is all real numbers if you've got a positive n. Okay? And this one should include 0, so it should say if n is less than or equal to 0, then you only get all reals except for 0. Okay, for the domain, the range is just from 0 up. It includes 0 if it's a positive power, and it doesn't include 0 if it's a negative power. If we have a fraction power which can be reduced, and it's down to odd over odd after you reduce it, then you get quadrants 1 and 3. Notice that if you take a negative to an odd power, you get a negative. Take an odd root of a negative, you get a negative. So that's third quadrant. And it turns out that the part in the third quadrant is just a rotated image of the part in the first quadrant. You rotate 180 degrees or half circle, pi radians about the origin. Okay, and that turns out to be quadrant 1 and 3, and so the graph has origin symmetry. The domain and range are both all reals for positive n's, and for negative n's, they're all reals except for 0. So when you put this together, there are basically 11 different possible shapes, and here they are. So again, the powers, each row has a different size of the power. At the top we have the positive powers, so in quadrant 1 those are all more or less the same, increasing concave up. N equals 1 is a very specific one, so that's why a couple of things are grayed out there. It's just y equals x, which you see over in the far right there on the second column, second row there of graphs. This row of graphs, 3 graphs here, is for n's between 0 and 1, and if you look at the first quadrant, they all look more or less the same, increasing concave down, go through 0, 0, 1, 1. And n equals 0 is a very specific one. It's a horizontal line with a hole in the graph at 0, 1. Otherwise, all the y's are 1. And n is less than 1. Negative ones all look the same in the first quadrant. This decreasing concave up thing with the vertical and horizontal asymptotes. And we have, now, so all those look the same in the first quadrant. Now, all of these in this first column here, quadrant 1 only, are no symmetry. That's where the power is irrational, or it's an odd over even rational number power, and those are quadrant 1 only. So that's all you get is the quadrant 1. Whereas these where you have an even over an odd power, then you get a reflected image here. So whatever the first quadrant looks like reflected over, and so notice you see reflections here in all 4 of these cases. And we have rotations in these 4 cases over here where you have an odd over an odd power. Rotate the first quadrant around to get the third quadrant, and you can see what you're going to get there. So some examples of powers that would work here. Let's see, this one here, the pi power would look like this first one here. This first one, if you can see where my cursor is moving there. So the upper left, or maybe the 7/2 power, that would be something like this. Y equals x squared is a good example of one that looks kind of like this one. y equals x cubed is one that looks like the next one over. Of course, this is exactly y equals x only. X to the first power, that is. This one could be like a square root of x, or y equals x to the 1/2 power would look like that. This one might be x to the 2/3 power. Might look like this one right here. And this last one over here would be like a cube root function, or y equals x to the 1/3 power. Might look like that one. This is y equals x to the 0, and this line by itself. And the last row, last line here, this first one, that would be a negative power, but negative 1/2 power would look like that, something, for example. This one here might be a negative power, but even over odd, negative 2/3, for example, or negative 4/3. Both would look kind of something like that. This last one would be odd over odd, so negative 3/5, negative 5/3 for the power would look something like that. Now, remember we can do transformations, and if you look at this formula, y equals a times x minus h, in parentheses, x minus h is in parentheses, to the n power, and then plus k. A, h, n, and k are constants. X is your input variable, y is your output variable. Well, when you see that, the first thing you should notice is not how different it is, but how the same it is. Notice that that should look just like y equals x to the n. And so the general shape is determined by that n. It's one of those 11 shapes that we just saw. So the n is the most important of those constants. It determines the basic shape of the graph, and those details we just looked at for the 11 different possibilities that we just saw on this previous slide. So depending on what the n is, we get one of these 11 shapes for the basic shape. But the other three numbers, call these things parameters, the h, k, and a, those constant numbers there, those determine how much we've transformed it. So notice the h says that we've replaced x by x minus h, so that's an amount of horizontal shift, a horizontal translation. So we're shifting to the right if h is positive and to the left if h is negative. Notice that the built-in negative sign. So if you see an x minus 2, then we've really shifted to the right 2, but if you see an x plus 3, we went to the left 3. Now the k, if you rewrote it, it would be y minus k equals a times x minus h to the n. So really this is a shift on the y. You're replacing y by y minus k, so this determines the amount of vertical translation. It's shifted up if k is positive and down if k is negative. Now a can do two things. It determines the amount of vertical strain, that is the expansion or compression vertically. You can stretch it or squish it up and down, closer or further away from the x-axis, and then you can also flip it over the x-axis. And the way you look at that is if the absolute value of a is less than 1, then we've had a compression. Everything is closer to the image points are closer to the x-axis than the pre-image points. Whereas if the absolute value of a is bigger than 1, we stretched it vertically, a vertical expansion, so the points and the image points are further away from the x-axis than the pre-image points. And if a is negative, then it flips over the x-axis from what we saw in the basic way. We're going to call this the basic way, and then it's flipped over upside down from the x-axis over the x-axis if a is negative. So that would be upside down from the standard, and in the standard's way, the normal side up from what we see here is what happens if a is positive. Okay? And so this is going to give you a transformed power function. So let's see if we can figure out a type of exercise here that we might do. These particular ones are done, and I'll tell you that n is either -1, -2, 0, 1, 2, or 3. I'll narrow it down that much for you. And these are power functions. There are 5 different ones here. And see if you can figure out what a, h, and k are. First, just figure out if it's positive or negative for each one. First, figure out what n is. You do that based on what shape you see. And then we figure out the sign, positive, negative, or 0 for a, h, and k. and then see if you can figure out the actual number for A, H, and K. Begin N first. So figure out those and then actually write down the formula for these equations. So there are 5 of them here. We're going to have you press pause here just a second and work these out, and then come back and then check your answers. Press pause now. Okay, so let's take a look at these now and see what you came up with. First of all, from the basic shape. You see this basic shape like this, you should recognize that as like a y equals x squared kind of shape. X cubed, well, that was going to be for this one here, and this is kind of the same shape upside down. And this one here, this green one's more like a y equals x cubed shape. And these other two here are also like x cubed that are upside down. So y equals x to the 1 would be a straight line. Okay, it's not that. Y equals x to 0 would be a horizontal line with a hole in it. It's not that. And negative powers would have vertical asymptotes and horizontal asymptotes. So it's not that. So these are going to be positive powers. They're one connected piece, so they're not negative or 0 powers. Okay, well, and they have some symmetry. Okay, so they're not negative, and so they're certainly not negative 2 or negative 1. And so these are it's going to be 2 and 3, and this is 2 on these two that are over here on the right, and these 3 on the left are 3 for the power. So that's just determined by the basic shape. Now if you look at this one here in blue, let's look at it. It's been shifted to the right and up, so H is positive, K is positive. And in fact, the coordinates of that vertex right there, that minimum, is HK. So H is 5 and K is 3. And this has been stretched a little vertically, but A is positive because the right side of the arrow here is pointing up, so it's still pointing up like normally the right side would be pointing up for y equals x squared. So you look at this arrow here that's, well, it's not really written as an arrow, but there should be one here on the right side, so it's going up forever, so that A is positive. This one down here, it's been shifted right and down, so H is positive, K is negative. Okay, so H is actually 6, K is negative 5, because that's the coordinates of that vertex right there. And the right arrow is pointing down, so it's been flipped upside down, so A is negative. Okay, we'll come back to what A actually is in just a second. Okay, let's look at this red one here, this maroon color, dark red. Now we see the basic odd shape with the arrows pointing, the sides pointing both ways. Now the inflection point was at the origin, so you can see the inflection point right here, and so you can see what the inflection point's been shifted from the origin. It's been shifted left and up, so H is negative, K is positive, and the coordinates of that inflection point are actually HK. So what's H? H is negative 4, K is 6. And it's been flipped upside down because the right arrow here is pointing down. Normally the right arrow pointed up, so this has been flipped over, so A is negative. Okay, we'll also check on the size of A in just a few minutes. This one's very similar. Odd power, so see that odd shape, so we see 3, odd over odd shape, with the power bigger than 1, so that's going to be power 3 in our case. There's the inflection point right there, so it's been shifted left and down, so H and K are both negative. Specifically, H is negative 6 and K is negative 2. That's the point is HK right there, which is negative 6, negative 2. And the right arrow is pointing down, so it's been flipped, so A is negative. A is positive on this one over here because the right arrow points up. It's not been flipped over. Okay? It's been shifted to the left, but not up and down. So, to the left means H is negative, not up and down at all, says K is 0. So that's negative 10, 0 is the coordinates of the inflection point. So that is HK, negative 10 and 0. And A is positive. Here are the actual formulas. Let's see how we actually came up. Well, I told you how we came up with almost all this. The only thing we haven't really talked about is the size of A. That's the hardest thing to come up with, but let's see if we can follow that. Think of this as your new origin right here, this point on this blue one, the vertex point right here, if you can see where my cursor is moving around there. So that's your new origin. When you go to the right one, normally you would go up 1, but in this time you go up 2. So that means it's been stretched twice as tall. Normally you go to left 1, normally you go up 1, now you're going up 2. Normally go to the left 1 from the vertex, right? Normally go left 2. You'd normally go up 2 squared would be 4. Now let's see if you go up 8. 1, 2, 4, 5, 6, 7, 8. Sure enough. So everything's twice as tall, twice as far from, it's been stretched twice as tall vertically, so that's going to be a 2 there. Let's look at the green one down here. Okay, that's the vertex. Normally go, first of all, A is negative because it's pointing down, it's been flipped over. Well, what about the absolute value of A? Right 1, normally you go down 1, looks like we've gone down a half. Let's see if we can find one that's on an integer value to be sure. There's a lattice point, one that has integer coordinates. Okay, so from the vertex, we go to the right 2. Now, normally we would go up 4, but now we're going down 2. Okay, so we take the, so negative 2 divided by the original 4 is negative 1/2, and that's kind of how you can figure it out. So here, we go to the right 1, we normally go up 1, and we were actually going up 2. So our 2 that we actually went up divided by the 1 that would normally go up gives us 2. This went down 2, okay, so that's negative 2, and normally we go up 4. Negative 2 divided by 4, that's the way you should do it. That's negative 1/2. So it's been compressed vertically. It doesn't go and right 1 down a half. So it's been compressed by a factor of negative 1/2. You see the 6, negative 5, that's the coordinates of the vertex right there. And so we see this transformed power function. We see the vertex now is at 6, negative 5, and it's been flipped upside down and squished by a factor of 1/2. Compressed vertically, a vertical strain. This one here, the vertex is 5, 2, so that's x minus 5 here, and then I said 2, I should have said 3 here, 1, 2, 3, and then the 2 is here. It's been expanded by factor 2. Alright, let's look at the red one here. We know the A is negative because it's been flipped over, but how much? Well, it's nice to find a lattice point if we can, and there's actually one. It's a little hard to see here, but we go to the right 1. It looks like we've gone down, well, less than a half, maybe a third. Let's go over 3 here. Normally you go down. Normally you go up 27. Let's see how far we go down. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that actually is a point going right through the graph. So this says we went to the right 3 and we went down 9 when normally we would go up 27. Well, down 9 is negative 9, and divide that by what it would normally do is up 27. That's negative 9 over 27. That's negative 1/3. That's our A. So it's been compressed by a factor of 1/3, negative 1/3. So normally it would be up 9 times negative 1/3 is down. Normally we go up 27. Excuse me. Normally we go up 27, multiply by this negative 1/3 here, and what do we get? Now it's only down 9. Okay. Similarly, and then of course the coordinates of the inflection point are the coordinates that you see here: negative 4, positive 6. Notice the one with the x, you got to change the sign on it because the minus is built in here. So negative 4 and then plus 6 are the coordinates of that inflection point. And the cube gives you that shape. Here again, the cube is the shape. The coordinates of the inflection point, according to this, are negative. Oh, that's a typo. Should be negative 6, negative 2. Alright, let me fix it. There we go. There we go. Yeah, negative. It should be negative 6, negative 2. I believe that's what we said earlier, and that's the coordinates right there of the inflection point. Now let's see if the rest of it's right. Everything's right except maybe this is negative. Okay, So it looks like maybe that's a fourth down instead of up 1, but let's go over here. Here's one that's right on a corner. So from here we go right 2 and down 2. Okay? So that's down 2 when you would normally go up, well, when you cube 2, it's 8. So that's be 8. So it's negative 2 over 8, which reduces to negative 1/4. So that's negative 1/4. It's been squished or compressed vertically by a factor of 1/4, and then flipped also. So check it out. If you go up 1 multiplied by negative 1/4, now you're going down 1/4. Go the right 2. Now you would normally go up 8, but now multiply by negative 1/4, and what does that give you? Down 2, and so forth. Okay, this one, notice the k is plus 0, so we just didn't even write that. And this is 2 times x plus 20 plus 20. No, it should be just 10. That's a typo. There we go, that's better. X plus 10 cubed. And the 2, we know it's positive because it's going up and down. Let's see if we should be able to see the 2 right here. Normally you go to the right 1, now we're going up 2. So you take the 2 that it's going up now, divide by what it normally goes up, 1, and that's 2. And so we see everything's been doubled. So when you go to the right 2, that would be cube that's 8. Now it should go up 16, which is off our screen, so we can't really check that one. Okay, so there we go. Let's do this again for the next, same kind of problem. We've got 3 more relations here, 3 more functions, power functions that have been transformed. So we started with some basic power functions and transformed them. I'll tell you, n is one of these numbers, negative 2, negative 1, 0, 1, 2, or 3. Pick out the n first, then figure out the values for a, h, and k. And first of all, just see if you can figure out if they're positive or negative. And then go in and figure out their values if you can. Okay? See if you can figure this one out. Press pause now. Okay. Let's look at F first, the blue one. Okay? Well, let's look at all of them. All of them are in 2 pieces, and they have vertical and horizontal asymptotes. The ones with vertical and horizontal asymptotes are the ones that have a negative power. So we've eliminated the powers of 0, 1, 2, and 3. The only choices now from the ones we're given are negative 2 or negative 1. Actually, there are lots of negative powers that have a very similar shape. It would be difficult to figure out which one it would be if I didn't narrow it down for you a bit. But I've narrowed it down to negative 2 or negative 1. So it's those negative powers, one of those 2. Now the negative 1, think of that's odd over odd, so that's going to have a rotated image, and so we're going to have it's going to have a rotational symmetry, and that's going to be true of the blue one, F. Now if it's negative 2, it's going to have a y-axis symmetry to begin with before we start shifting it around. So it's still going to have some line of symmetry. It'll be symmetric about its asymptote, and that will be it'll be a reflective symmetry, and so that's true of the green one, M, and the red one, G. So M and G are power negative 2 for N, and the power is negative 1 for the blue one, F. Now, normally the origin is at the intersection of the 2 asymptotes, the x and y axes, remember? Okay, so you can find out HK by finding out where the origin gets mapped to, whether it's actually part of the graph or not. In this case, the origin was not part of the original graph, but it was an important point in relation to the graph because it's where the 2 asymptotes meet. So HK is now going to be the point where the 2 asymptotes meet. And notice on this one you can see a vertical asymptote here at 3. So H is 3. And we have a horizontal asymptote at 2. Y equals 2. So K equals 2. So 2, this point right here, 2 3 is the point HK. H is 2, and I'm sorry, H is 3, and K is 2. It's the point 3, 2. That's what I should have said. The point 3, 2. H is 3, K is 2. Now what about A? Well, normally when you go to the right side of the asymptote, the arrow coming into the asymptote is pointing up, and that's still true here, so A is positive. And in fact, A is just 1 because when you go to the right one, we're still going up 1, so it's not from right one from that where the origin got moved to here. So go from where the asymptotes meet. We go right 1, we're still up 1, so A is still just 1. How about so there's the actual formula. Hopefully I've got this right. Okay, it's a little hard to see there. That's -1 for the power. Let's see if I can actually fix that while I've got my mind on it. Move it just a little bit. There, that's a little bit easier to see. And notice that we went to the right 3 and up 2. And so our new intersection of the asymptotes is right here at 3, 2. So there's why it says x minus 3 and plus 2. It's a -1 for our power. For the ones that we gave, that's the only one's going to have a vertical and horizontal asymptotes and a rotated image around to here. And it didn't get stretched or flipped any, so it's just 1 for the coefficient. In fact, none of these got stretched or compressed, so they're either 1 or -1 for the coefficients. All right, the green one here, M, notice that we shifted to the left and up, so H is negative, K is positive. And again, where the asymptotes meet is the HK. So the asymptotes meet right here. So we can see the horizontal asymptote here, that's at 4. So that tells us that it's been shifted up 4, so K is 4, that's this one out here. And it's been shifted left 1, 2, I should say 3, not 4. I've got a typo there. 3, this should be 3 right here. -3. So this is actually -3, 4. So that's a mistake. Let's fix that. So with that being -3, that makes this one +3 here. There we go. That one looks good now. And so that's -3, 4 are the coordinates of that where the asymptotes meet, which is right there. Notice on the right side of the asymptote, it's going up. That's the normal shape that you see here, decreasing concave up on the upper right. And so that is going to be a positive A. And notice from the vertex, or not the vertex, but the where the asymptotes intersect right here, which is where the origins got moved, right 1, still up 1, so its A is just 1. So that's good. That one's fine. Okay, I got this one right. X plus 3 and then -4 here. And both of these were power -2 because they reflect over that vertical asymptote. So that's that even power going on there, even over odd. Reflective symmetry. So notice that the origin got moved left 3 and down 4. Okay, and so that makes this x plus 3 and makes this -4 on the outside. However, notice on the right side of the asymptote, the arrow is pointing down, so it's been flipped over the x-axis at some point in the process, and so we have now, see it's upside down, so that's a negative power here. You go to the right one, it's still down 1 instead of up 1, so that coefficient is actually just -1. So we can actually do problems like this where we see the transformed relation and then we come up with the formula. We can also do problems like this one here. Start with something basic like y equals x squared, h of x equals x squared, and we want to translate the relation in this order. Translate this relation 2 units up. Then take that transformed relation and reflect it about the x-axis. Take that transformed relation and end it by translating it 3 units to the right. So do those 1, 2, 3 transformations. So you're going to have four different graphs and tables and so forth all together. The original, its image under the first one, which is going to be the pre-image for the next step, and then its image, which is then the next step is the image of the one before, and it's the pre-image for the next, and so on until we end with the very last one. And so make a little table of some key values, some that are interesting, like say just the integer values from -2 to 2 is fine, and then find all those for the inputs, and make a little table of say those 5 values, and track what happens to those 5 values as you go through each of those transformations. So you're tracking what's happening numerically in the table, or with the actual points, and pre-image to image. And then track what happens in the formula as well as we make each of these, and describe in words what happens to the graph, which we've actually already got, and then actually show the graph for each of the ones. It's best if you get some about 4 colored pencils here, and do everything color coordinated. So see if you can do this one on your own now. Press pause now. Well, here's what we get. The original function is y equals x squared, and some key points on that might be -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And then we get the blue graph that you see on the graph below. Okay? Next, I want to shift it up 2 units, a vertical translation by 2 units. That's a vertical thing, so we're going to be changing y and leaving x alone. So leave x alone and replace y by y minus 2 in the formula, because remember the formula is backwards. If we go up 2, what we're really doing is adding 2 to each y coordinate, but in the formula we replace y by y minus 2. So it becomes y minus 2 equals x squared. That's going to be the pink graph. Now, we might want to solve that for y, so I'm going to go ahead and do that. Solve for y by adding 2 to both sides of the equation. So whether we write it y minus 2 equals x squared or y equals x squared plus 2, it's the same relation, the same function, the same set of ordered pairs, the same graph. In the table, we're going to leave the x's alone, and we're going to add 2 to the y coordinates. So notice -2, 4 becomes -2, 6. -1, 1 becomes -1, 3. 0, 0 becomes 0, 2. 1, 1 becomes 1, 3. And 2, 4 is mapped to 2, 6. And so every point is moved straight up 2 units to become the pink graph that you see below. And so we see the blue graph is just shifted up 2 units to become the pink graph in the picture. Now from the pink graph, transform it to become the green one. We're not going back to the original and transforming it. We're doing a composition of transformations here, so that the output from one becomes the input from the next. So the pink one was the image of the blue one under the first transformation, but the pink one's going to be the pre-image for the transformation the next time, and its image is going to be the green graph. So we're going to reflect the pink one over the x-axis. Now to do that, we change the sign on y. So in the formula, that is, replace y by minus y, leave x alone. So I had it in the form y equals x squared plus 2. Now in that form, I'm going to replace y by minus y, and that becomes minus y equals x squared plus 2. Now if I solve for y here, I want to multiply both sides of the equation by -1, and I get y, and distribute on the right side. So I get y equals -x squared minus 2. In the table, we're going to change the sign on each y coordinate, leave the x coordinates alone. So we had -2, 6. It now becomes -2, -6. -1, 3 becomes -1, -3. 0, 2 becomes 0, -2. 1, 3 becomes 1, -3. And 2, 6 becomes 2, -6. And we can see each point is moved straight down across the x-axis, the same distance on the other side of the x-axis as it was before, but on the other side, and that gives us a reflection over the line y equals 0, the x-axis. So the green one becomes the image of that step. Now the green one's going to become the pre-image for the next step as we shift it to the right 3. Okay? So Going right 3, we're going to actually add 3 to each x coordinate, leave the y's alone. So negative 2, negative 6. The negative 6 is going to be left alone, but we're going to add 3 to negative 2 to become 1, negative 6. Similarly, we add 3 to negative 1 to change negative 1, negative 3 to 2, negative 3. 0 to negative 2 goes to 3, negative 2. 1, negative 3 goes to 4, negative 3. And 2, negative 6, when we add 3 to the 2, we get 5, negative 6. So we're really adding 3 to each x coordinate, but in the formula you replace x by x minus 3, and so you'd write this as y equals negative on the outside, x minus 3 in the parentheses squared minus 2. And notice that this is just like the last problem. So in the final, we see our final graph down here in the red, the dark red, the maroon, and notice that the vertex is 3, negative 2, and you can see that in the form of the formula that we have here. Positive 3, opposite sign of what you see here in this formula. So it's positive 3, then negative 2 are the coordinates of the vertex. It's been flipped upside down here, but not stretched any. Alright, let's go change a little bit. Remember back when we talked about linear functions, this is actually a slide that we've used earlier. We talked about direct variation or direct proportion. This is some language for expressing a linear equation through the origin. So we could say y equals mx plus 0, right, goes through the origin, or just y equals mx. Or sometimes instead of m, we'll call it k when we're talking about direct variations. So we say y varies directly as x, or just y varies as x, means y equals some constant times x. Y equals kx, y equals mx, write it either way, same thing. K or m is a specific constant. Y is proportional to x, or y is directly proportional to x, is another way of saying the same thing. So the k, which is the slope in this case, is the proportionality constant, or the constant of variation. And these particular ones are going to include the origin. So what we're doing here is really, if you want to think of it as a transformation, we're just thinking of y equals x, and we're only doing a vertical stretch or compression, a vertical strain. So we're not doing any kind of other transformation to this other than this one multiplication. Okay, so that's a direct variation. And notice if you don't see the word direct, if you don't see the word indirect, direct is implied. We're going to talk about inverse, the word inverse I should have said. The inverse variation is, we're going to see what that is today, and then also talk about direct variation. So again, if you don't see the word inversely, then we're talking about directly proportional, okay, and the directly may or may not be said. So we can generalize this idea a little bit to power functions. So for example, let's just look at the language here. We can say y is directly proportional to the square of x, or we can leave out the word directly and it means the same thing. Y is proportional to the square of x. When you see y is proportional to, that means y equals k, and then times whatever's next, the square of x. So y equals k times x squared for some constant k. So notice that's just a y equals x squared, a basic power function that has a vertical stretch to it. Possibly a negative k would be a flip, but vertical stretch or compression, a vertical strain. Okay? Now, when you see the word inversely in there, y varies inversely as x. Again, when you say y varies, it's y equals k, but when it says inversely as x, we're dividing by x. So that means y equals k divided by x, which also is a power function, because you can rewrite that as y equals k times x to the negative 1. It's not a basic power function, it's one that's been transformed, but only one transformation, a vertical, well, perhaps two transformations. If k is negative, it's been flipped, and if k is not, absolute value is not 1, then it's been stretched or compressed. So, depending on how you look at that, one or two transformations there. Y equals k times x to the negative 1, or k divided by x. So the inversely gives you a division, which basically is a negative power. So another example, y varies inversely as the square of x, y equals k over x squared, or y equals k times x to the negative 2. You can say that either way. y is proportional to the cube of x, y equals k times x cubed. Y is inversely proportional to the fourth power of x, y equals k divided by x to the fourth, or y equals k times x to the negative 4. So you can see that these give us transformations of power functions. We can see this language oftentimes used by scientists. For example, scientists talk about an inverse square law quite a bit. We'll say y varies inversely as the square of x. This is used for things like gravity. Electrical charges obey an inverse square kind of relationship. We can also have what we call joint variation when there's more than one output, more than one input leading to an output. So if we have z varies jointly as x and y, that means z varies, so that's z equals k. Jointly will be, you don't see the word inverse, so it's all multiplication, but jointly as x and y, so you multiply by both x and y. Z varies jointly as x and y means z equals some constant times x times y. So here's a real-world example that you're going to see in science. This is Boyle's law. Volume is directly proportional to temperature and inversely proportional to pressure. If we use sort of obvious letters there, V for volume, T for temperature, P for pressure, this says volume equals K. It's directly proportional to temperature, so that's times T. Inversely proportional to pressure, so that's divided by P. Notice that this means that when we increase temperature, we increase the volume if we hold the pressure steady. If we hold the temperature steady and increase the pressure, we're going to decrease the volume. And that should make some sense in terms of your personal experience. Okay? So, for example, think of your car tires. If the temperature is warmer, then it's going to increase the volume if the pressure stays the same. Okay? Or if you put more air in them, you increase the pressure, and the volume is going to increase, and the pressure is decreased if the temperature stays the same. Okay, so let's take a look here at an example. Well, here's another inverse square law. The intensity I of light projected on a screen is inversely proportional to the square of the distance d from the source to the screen. The intensity is 90 watts per square meter at a distance of 5 meters. That last sentence is what we call an initial condition. If we know the first sentence is going to allow us to get an equation, but it's going to have a constant k in there. We don't know what that constant is yet, but it is a fixed number. If we know a particular ID pair, which the second sentence gives us, then we can plug that in and solve for our constant k. Then we know the equation. Once we have the equation, then if we know d, we can solve for I, or I, we can solve for d, and that's exactly what these questions are asking us to do. So I think you should be able to do this now based on what we've seen so far. Press pause now and work this out. Okay, well, let's see. I is inversely proportional to I equals k divided by, what, the square of d. So that gives us, look over here in the bottom left, whoops, bottom left here, I is k divided by the square of d. I equals k over d squared. So that's our formula, but we just don't know what k is. So to solve for k, we know that we can substitute I as 90 at the same time we substitute d as 5, and it should work out. And I'm actually going to work in the units here because I want you to notice that k actually has some units. K typically does have units. I is 90 watts per square meter. That's W over M squared. And that equals k over, and d is 5 meters, so it's 5 meters under the square. So when you square 5 meters, you get 25 square meters. And we multiply both sides of the equation by 25 square meters to get k by itself. And I switch sides also. So move k to the left too. So k equals 25 square meters times 90 watts per square meter. Notice that the square meters cancel, and so we get watts. And 25 times 90 is 2,250. So k is 2,250 watts. So I is 2,250. Probably should go ahead and say watts there over d squared. So if you plug in d in meters, then I is going to be in watts per square meter. So our formula I as a function of d is 2,250 actually watts over d squared. Okay, so now that we have the formula, if we know what's the intensity if the distance is 10 meters, we just plug in 10 meters and we get watts per square meter then for our intensity. And I'm going to leave out the units for a second and put d as 10. 10 squared is 100. Divide 2,250 by 100, you get 22.5. And so the intensity is 22.5 watts per square meter. On the other hand, the next one, what would the distance be that we need to place the screen if we want the intensity to be 100 watts per square meter? So this time we know the 100 goes in place of the I, and we solve for d. Multiply both sides of the equation by d squared. Divide by 100. D squared is 22.5. So d is the square root of 22.5. Actually, when you take the square root of both sides, we should get absolute value of d, which would give us plus or minus here, but intensity is not negative. So in the context of the problem, we know we can eliminate the plus, we can eliminate the minus. We don't need the plus or the minus, just the plus only. So d is the square root of 22.5, which is approximately 4.74, and that's in meters. So notice in general, this is how you work a variation problem, direct, indirect, whatever. You set up the equation first using knowing how to transform the language into an equation, which is what we saw back on this slide here. And then what we do once we have that, we take a initial condition, plug in for the unknowns, and solve for the constant, which is unknown but not variable. Once that constant is found, that constant is constant, meaning it stays the same as we change I and d. That k stays the same. And so in our formula, that's fixed. We didn't know what it was at first. Initial condition allowed us to find it. Once we found it, it stays fixed. So then if you plug in all the variables except for one, hopefully we can solve for that last variable. All right, one final category of problems that we want to look at here. Recall that we use least squares linear regression capabilities of your graphing calculator to find the equation of the line that best fit a set of data. And we talked about that a considerable amount in the linear equation, linear functions unit. Often a set of data is modeled quite well by a linear equation. And since the linear equation is the simplest model and it often works quite well, it's very often the model of choice. However, we can look at a scatter plot sometimes and we'll see that the overall shape of the graph doesn't really look like a line too much, but it maybe has a pattern to it that is more like some other type of function. When this happens, it's often worth the added complexity of going to a more complicated model, a more complicated formula. It's better to do that, to switch to that type of model, than to stay with something simple like a linear equation. So if that's the case, we can do that. Now, as we go through this course and we study different classes of functions, we'll use the calculator in each case to obtain the regression equations for that class of functions, at least for all of them that the calculator has available. So one of the things that a calculator will be able to find regression equations for, besides lines, is a power function. Specifically, these direct variation kind of problems, where we have a power function of the form y equals a times x to the b power. Now, this particular one only works when we have essentially first quadrant graphs, so only positive x and y. If you try to perform this power function regression and either an x or y or 0 or negative, even one of them, then it's going to give you an error message. But if you only have positive inputs and positive outputs, strictly positive, not 0, not negatives, then, and you see a shape that looks like it might be one of the first quadrant shapes that we know about for power functions, one of these shapes, let me go back real fast, way back. Yeah, one of these shapes. Not the linear one so much, because we can just use linear regression for that. But if it looks like this shape down here in the bottom, negative power, or this increasing concave up, like this first one, or increasing concave down like the one here, or this shape here, if it looks like one of those shapes, then we can use that regression capabilities of our calculator, and we will get a formula that looks like this, and it will figure out those constants A and B. Actually, what I've been calling A and N most of the time before, but instead of N, it's going to call it B. And the graph will only graph the first quadrant of the graph, regardless of what it comes up with for the power. Even if the power is practically 3, or exactly 3 even, it's not going to graph first and third quadrant. Now let's remember the steps for regression of the TI calculator, and these are the steps for a TI-84 or an 83, and they're very similar for a void. Okay, here's what we want to do. Same steps we use for linear, except for one spot, which we're going to talk about here. So we're going to press Stat, and then choose number 1, which is Edit. Place the cursor up on the label L1, press Clear, and Enter. Right arrow the cursor over to the label on label 2, L2, press Clear, and Enter. That way you know you've got 2 clear lists, so clear those out first. Then put your cursor back in list 1 in the first spot, and type in your first x value. Hit Enter. Second x value. Enter. Enter all your x values in list 1. Then right arrow over to list 2, and in the same order, type in the corresponding y values and hit Enter. So your x's are in list 1, your y's are in list 2. Now, you should have already set up plot 1, so it's a scatter plot, and L1 is x's and L2 is y's, and I like to use a little box. And so do that first. Once you've done that once at the beginning of the course, hopefully you did that back in the linear section, just leave it alone. If you haven't changed it from when we did this before, you won't have to do that setup again. Okay? All you have to do is turn plot 1 on by pressing y equals, go up to where it says plot 1, get your cursor on it, and hit Enter. If it's got a dark background and a light letters saying plot 1 with a dark background, it's turned on. If it's a light background and the letters are dark, saying plot 1, it's turned off. Be sure to turn it off when you're finished. So turn it on when you need it, turn it off when you're finished. Then press Zoom 9, which is Zoom Stat, and that will graph it for the scatter plot for you. By the way, I didn't write it down here, but one thing you might want to also do as you're in Y1, y equals turning on plot 1, you may want to delete or turn off all of your Y1, Y2, and so forth. So the only thing you're going to see at this point is the scatter plot. Now then, here is where I've got this bold-face thing. Look at the basic shape of the scatter plot and choose an appropriate model. So now we have multiple models to choose from. Back before, we were only choosing linear. Okay, and we kind of said, well, was linear good or not? But we didn't really have any others to choose from. Now we can choose linear if it's the most appropriate. And if the thing is pretty close to linear, go ahead and use linear because it's the easiest one to use. But if we have a pronounced concavity to it, then you're going to want to use, say, maybe a power function if a power function looks like it might work. Now again, you can only use the power function if your data is first quadrant only data. Positive x's and positive y's, no zeros, no negatives. So if that kind of data, and we can see a pretty consistent all concave up or all concave down kind of a shape to it, then maybe we want to try a power function. So press Stat, go right arrow to calculate, and go down, and there's a list of different models you can choose from. You'll see linear down there, and if you arrow down far enough, you'll get to one that says power. I think it says PWR for power function. And say if it's a power function, choose that one. If it's linear, choose that one. As we look at other types of graphs and of course later on, you'll have more to choose from. And we'll be going back over this regression every single unit. So once you do that, you're going to type that in. If you've got the older operating system, it will come up and it'll say, like say power regression, and you type in L1, comma, that should say L2. Let's fix that. L1, L2, and then Y1. Okay, and so that's X list, Y list, and where you're going to put your equation. If you got the newer operating system, you don't have to remember the order. It comes up with a little wizard that where you fill in the boxes, and so it says X's, and you type L1. It asks you for where your Y's are. You type in L2. And remember, you can't type in an L and a 1. You have to type in L1 by second 1, and L2 is second 2. And Y1, you can't type a Y and a 1. You get your Y1 from either going to variables, right arrow to Y variables, choose function, and the 1. If you got the newer operating system, there's a shortcut by hitting alpha, and then I think it's trace, which will give you a list of the different Y1, Y2, and choose it from that. But that when it says store equation or something like that, you put Y1 there. Then you hit enter, and it will do a couple of things. It'll store the equation in Y1, and your diagnostic should be turned on, so it's going to display an R-square value that's going to give you an accuracy of your fit, and it's also going to tell you what your parameter, your constants are. In this, if it's a linear regression, well, if it's linear or power function, there's two of them. It'll give you an A and a B, and it tells you where to put them in the formula. Then if you press graph next, you're going to see the graph of the equation that you came up with on top of the graph of the scatter plot, and you can see how closely it comes to hitting the points in the scatter plot. Let's look at an example. So see if you can do this. We've done linear regression before, so when you graph this one, you're going to find out that a line's not going to be there. It's going to be more appropriate to use a power function, and you need to see why that's true. So, but otherwise the steps are the same as the linear regression. So you should be able to do this problem. Go ahead and do this now. Press pause. Okay, so first thing we do is we go, let's look at the picture here. We go to our calculator. Okay, we go to L1, press clear and enter. L2, clear and enter. Enter our data in. 25, enter. 28, enter. 32, enter. 35.5, enter, and so forth. Get all the X's in. Right arrow to L2. Press the Y's in the same order, of course. They got to match up. So you see the order pairs lined up here. And so then 141, enter. 198, enter. 295, enter, and so forth. So by the way, this is mass in grams and length in centimeter of a certain species of fish. And we're going to see if we can find a relationship here. Then we press our scatter plot by saying turn on plot 1. Okay, so you hit Y equals. I just cleared out everything else, and originally there was nothing here, and you can see the plot 1 is turned on, and I did that first, and then hit zoom 9, which is zoom stat, and you see the graph of the scatter plot here in the second screen. Now, Y is, we could do a linear model for this, and it may not be too bad of a fit, but why is a power function better? Well, I think you can see a distinct and consistent concave up shape to this, which says that maybe some other model might be a better fit. Okay? And so we might pick a power function for this one. Everything's in the first quadrant, positive x's, positive y's. The first quadrant will give us some kind of an answer. Let's see how it works. So then we go to stat, right arrow to calc, and we go down and see power regression, which is actually A. And then we enter it in. It'll actually, if you have the older operating system, it'll be power regression, L1, comma L2, comma Y1. If you got the newer operating system, it looks like this screen here, which will say X list, and you tell it L1, Y list is L2. Frequency list, just leave it blank. And regression equation, store in Y1, and then put your cursor on calculated, hit enter. And you'll see this screen down here in the lower left come up, It's the formula is y equals a times x to the b, and a is 0.0095681723. B is 2.978848003. R square value is 0.999, so 99.9% of the variation in the data is explained by this model. So that's a very good fit. If the R square is close to 1, it's going to be a very good fit. If R square is close to 0, it's a very, very bad fit. Okay? Well, this R square is very close to 1, so this is a quite good fit, and that's also corroborated whenever you push the graph, because when you push the graph button, remember this has been stored as y1. You can see it right here in the screen over here, and when you graph it, notice that the graph comes very close to, not perfectly on, but very close to the actual data values. So this is a very good, this model can be used very well to approximate this and to work this out. I do want to change one thing here. Let's write down our formula. I'm going to actually I used L. You know what? I think I'm going to use capital L. Lowercase l just looks a little bit too much like a 1. Okay, so that's capital L now. And so there's our formula. The L is our input, and the M is the output. I need to change it in the table. Why not? Go ahead and get it now so I don't forget. So L is our input, like our X, and the M is the output, like our Y, but we use L and M because they're more suggestive. L is the length, M is the mass, so that's a better way to do it. And so we get this. If I round off to 4 significant digits, that's 0.009568 times L to the power 2.979. Now the next thing is, how much would the mass be of a fish that's 30 centimeters long? Well, I just plug in 34 in place of L and solve for M, and that's easily done on the calculator because I just hit trace. So I hit trace. I make sure I'm not tracing the to the scatter plot. I may have to use my up or down arrows to make sure I'm on Y1, and you can see Y1 is formula here. And I just type in X equal. I just type in 34 and enter, and notice it takes me to that point. Where is that on the graph? Can you see it? I don't know if I can see it here or not. Anyway, it's on here somewhere. It was probably a flashing cursor, and it didn't come up across on the when I moved it over here. But there's a flashing cursor there, and that's going to happen when X is 34, and Y, or it may not be flashing, but there'll be a mark there. And X is 34, and here's Y, about 349. So that says when the length is 34 centimeters, the mass is going to be 349 grams. Well, let's do it backwards. What if the mass is 700? We put 700 in place of M. We could solve this by hand. We just divide by this coefficient and then take the 1 over this power, and that's going to give it to us. But we can also have the calculator do it by letting Y2 be the thing that we want, 700, and do a calculate intersect where that intersects our model, and there's the Y, but now the X is 42.9 centimeters. So according to this model, we would expect a fish that has a mass of 700 grams to have a length of 42.9 centimeters. Now I want to point out one more thing about why the power is essentially 3. Okay, the model gave us just slightly off of 3, but a power of 3 makes sense because think about the relationship between length and volume. Okay, volume is essentially a cubed of a length. If you take a sphere is the volume is proportional to the length, the radius of the sphere. It's 4/3 times pi times r cubed. Okay, and if you take a cube, a cube is proportional to the cube. The volume is proportional to the length, the cube of the length of the side. So it's the side cubed is the volume. So basically, volumes are more or less cubes of lengths, and so we would think that the volume would be proportional to the cube of the length, and the mass is directly proportional to the volume. The more the volume you have, the mass should be about more or less directly proportional. So it makes sense that the mass should be proportional to the cube of the length. And that's almost what we have here. We have the mass proportional to not length to the third power, but length to the 2.979 power, approximately cubed there. So very, very close to a cube, and that makes sense in the context of the problem. So here we've come to the end. What kind of goals and objectives should we have? Well, what should you be able to do? Well, you should be able to state the general formula for a transformed power function and understand the meaning of each of those constants in there. Describe the transformations of a power function and track these changes in the table, formula, and the graph, and describe these changes algebraically, numerically, graphically, and verbally. So if I give you a formula for a transformed power function, you should be able to find the graph, a table, and a verbal description. If I give you a verbal description, you should be able to track those changes. If I verbally describe those transformations, you should be able to track them in the table, and the form, and the graph. If I give you a graph of a transformed power function, you should be able to go back and find the formula for it. You should be able to understand and apply the language of variation or proportion, okay, as they apply to power functions with a vertical strain. So we can say, you know, like y is proportional to the cube of x, or like we just said in the last one, the mass of the fish was proportional to the cube of its length, or at least approximately. That's what we found. Okay, and apply these in real-world problem solving. We should also be able to use a calculator to compute the regression equation for a power function equation with a vertical strain, and use these to model real-world data and to solve application problems.